Why does clamping force even matter this much? Here's the simple version. When molten aluminum is injected into a mold under intense pressure, that pressure creates a force trying to push the two halves of the mold apart. If the clamping force holding those two halves together isn't strong enough, the mold can separate at exactly the wrong moment, ruining the part and potentially causing molten metal to escape. Which is obviously a serious safety hazard on a factory floor. The bigger the component being cast, the more surface area is involved, and the more overwhelming that separating force becomes. So if Tesla wants to cast a bigger, more complete section of a car body in a single shot, it needs proportionally more clamping force to keep everything locked together while the metal solidifies. Has Tesla actually found the limit of physics, as Musk once joked about? Probably not literally, but they've clearly found the outer edge of what's currently practical for automotive manufacturing, and that alone is a massive engineering achievement. It's also worth pointing out just how quickly this progression has happened. Tesla's first-generation Gigapress, introduced around 2020, operated at roughly 6,000 tons and was already considered a radical departure from how the rest of the industry built cars. Within just a few years, Tesla pushed to 9,000-ton machines for expanded applications. And now, barely half a decade later, the company is preparing to install a machine more than 5 times larger than that. For comparison, most conventional die-casting machines used elsewhere in the automotive industry for smaller components like transmission housings or engine blocks typically range from a few hundred tons up to around 4,000 tons. 50,000 tons isn't just bigger than what Tesla was using before. It's operating in a size category that, until recently, simply didn't exist anywhere in mainstream vehicle manufacturing. Design details. Rethinking how a car body is built. Here's where things get genuinely interesting, because this machine isn't just about raw power, it's about total production speed. Musk has stated that the goal behind this new Gigapress is to push automotive manufacturing speeds closer to what you'd see on an electronics assembly line, with each casting cycle potentially completed in around 5 seconds, and with the capability to produce multiple structural components within a single operational cycle. Stop and think about how radical that actually is. A traditional car body is built from hundreds of individually stamped metal panels, which are then welded, bolted, riveted, and glued together by an army of robotic arms working in careful sequence. Tesla's approach flips that entire manufacturing philosophy on its head. Instead of assembling dozens or hundreds of small pieces into a finished structure, Tesla wants to pour one enormous piece and skip most of that assembly process altogether. Based on details that have circulated from Tesla's engineering discussions, the upcoming Cybercab, Tesla's dedicated 2-seat Robotaxi, is reportedly being designed around roughly 80 major structural components. Compare that to the Model Y, which uses closer to 200 structural components in its body. That's a reduction of well over half the individual parts. Fewer parts translate directly into fewer welds, fewer mechanical joints, fewer robots required on the line, and fewer points along the way where a defect or misalignment could occur. The physical process behind this is genuinely impressive when you break it down step by step. Aluminum, including recycled material, recovered from previous casting cycles, is melted down at temperatures close to 850 degrees Celsius, or about 1560 degrees Fahrenheit. It's then transferred into a secondary holding furnace where the temperature is carefully maintained so the metal is always ready for the next injection cycle without needing to be reheated from scratch. Before that molten aluminum ever reaches the mold, it goes through a purification stage. Trapped gases are removed using a controlled argon degassing process, and the metal passes through silicon carbide filters designed to catch larger impurities. This step matters enormously because even a microscopic pocket of trapped gas inside a large structural casting could weaken the entire part in ways that wouldn't be visible until, potentially, a crash. The mold itself is prepared with a thin layer of lubricant to make sure the finished part can be removed cleanly. The air inside the mold cavity is vacuumed out before injection to prevent air pockets from forming during the pour. Then, in a matter of milliseconds, a high-speed piston drives the molten aluminum into the mold under enormous pressure. The engineering challenge here is genuinely delicate. Inject the metal too quickly, and you risk trapping air bubbles or creating flow-related defects. Inject it too slowly, and the aluminum begins cooling and solidifying before it has fully filled every section of the mold, which can turn an entire multi-hundred-pound casting into scrap metal. Once the casting is complete, the part, still sitting somewhere close to 400 degrees Celsius, or about 750 degrees Fahrenheit, passes through a rapid cooling system while the mold itself is cleaned, inspected, and prepared for its next cycle. According to available technical details, Tesla has managed to compress this entire sequence down to roughly 1 to 2 minutes between casting cycles size, which is an extraordinary pace given the size of the parts involved. Excess material gets trimmed off and fed directly back into the melting furnace to minimize waste. And every finished casting is inspected using X-ray imaging to catch any internal defects that would otherwise be completely invisible to the human eye. Powertrain and technical specifications. The Cybercab. Itself. So how does all of this manufacturing innovation actually translate into the vehicle you'd eventually see on the road? The Cybercab, Tesla's purpose-built Robotaxi, is expected to be the first production vehicle to use this 50,000-ton Gigapress at meaningful scale. Tesla has publicly targeted a starting price under $30,000 for the Cybercab, which would place it well below the average transaction price for a new vehicle in the United States, currently sitting above $48,000 according to recent industry data. The Cybercab is designed as a two-seat vehicle with no steering wheel and no pedals whatsoever, built entirely around Tesla's full self-driving software stack, rather than around a human driver. Tesla has stated it's targeting an operating cost as low as 20 cents per mile once the vehicle reaches full production scale and is deployed as part of an autonomous ride. Hailing network, a figure clearly aimed at undercutting traditional taxi and ride-share pricing by a wide margin. On the battery side, Tesla is expected to continue relying on its 4680 cylindrical battery cells, the same cell architecture first introduced with the Cybertruck and later adopted in updated versions of the Model Y. These cells are designed to deliver higher energy density and lower manufacturing cost per kilowatt hour compared to Tesla's earlier 2170 cell format. Tesla has previously stated a long-term goal of cutting battery cell costs by more than 50% through a combination of this new cell architecture and structural battery pack integration, a design approach in which the battery pack itself becomes a load-bearing part of the vehicle's chassis rather than simply sitting underneath it. And here's where the strategy really comes together. If the battery pack is structural and the front and rear sections of the body are each a single massive aluminum casting, you start to see the complete picture. Tesla isn't just trying to build a cheaper car by cutting corners on materials. It's trying to build a fundamentally simpler car with dramatically fewer individual systems that require separate assembly, separate quality checks, and separate points of potential failure. Range and charging performance. Because the Cybercab is designed specifically as a low-cost, high-utilization robotaxi rather than a long-distance personal vehicle, Tesla has indicated a target range somewhere in the neighborhood of 200 to 300 miles per charge. For most people shopping for a personal EV, that might sound modest compared to Tesla's longer-range Model S or Model 3 variants. But for a vehicle designed to handle short to medium urban and suburban ride, hailing trips, cycling back to a charging hub frequently throughout the day, that range is more than sufficient. Charging is expected to rely on Tesla's existing supercharger network, which by now includes more than 60,000 individual supercharger stalls positioned around the world. The newest generation, known as V4 superchargers, are capable of delivering peak charging speeds that can add well over 50 miles of range in roughly 15 minutes for compatible vehicles. For a personal car, that's already impressive. But for a fleet vehicle whose entire business model depends on staying on the road and earning revenue as many hours per day as possible, fast and reliable charging isn't a nice-to-have feature. It's the backbone of the entire economic case for the vehicle. How Tesla stacks up against the competition. Now, is Tesla actually alone out here, pushing the boundaries of both manufacturing and autonomy at the same time? Not even close. Let's talk honestly about who else is competing in this space, because fair credit matters, and Tesla certainly isn't working in a vacuum. First, there's Waymo, owned by Alphabet. Waymo has been quietly running fully driverless robotaxi services in cities including Phoenix, San Francisco, and Los Angeles for several years now, and it currently completes well over 100,000 paid rider trips per week across its active markets. Unlike Tesla's camera-only approach, Waymo relies heavily on LiDAR sensors layered alongside cameras and radar, a strategy many engineers consider more conservative, but also more thoroughly proven in real-world autonomous operation over a longer track record. Then there's General Motors' Cruise division, which has experienced significant setbacks, including a major suspension of its entire robotaxi operation in 2023 following a serious safety incident involving a pedestrian. Cruise has since been restructuring and scaling back its autonomous ambitions considerably. It's a sobering reminder that this technology, regardless of which company is building it, carries very real risks and very real consequences when something goes wrong. On the pure manufacturing and sales side, Chinese automaker BYD has emerged as Tesla's single biggest global rival, and in some recent quarters has actually outsold Tesla worldwide, once you include plug-in hybrid vehicles in the total count. BYD has also been investing heavily in its own vertical integration strategy and large-scale casting technology. though not yet at the 50,000-ton scale that Tesla is now targeting with this newest Gigapress. Toyota, historically one of the more skeptical major automakers when it comes to Tesla's manufacturing philosophy, has actually begun quietly adopting its own gigacasting techniques for upcoming EV platforms. A fairly clear signal that even Tesla's harshest critics recognize this approach might be onto something significant. And then there's Rivian, which has continued relying on more traditional modular manufacturing methods, betting that flexibility, easier repairability, and a more conventional supply chain will ultimately matter more to customers and fleet buyers than raw production speed. There's one more name worth mentioning here, Zoox, the autonomous vehicle company owned by Amazon. Zoox has taken a somewhat different approach from all of the above, designing its Robotaxi from scratch as a symmetrical purpose-built pod with no traditional front or back, rather than adapting an existing car platform. It's been running limited public rider testing in cities like Las Vegas and San Francisco, and while its production volume is nowhere near Tesla's scale ambitions, it represents yet another company betting that purpose-built Robotaxi hardware, rather than a retrofitted personal car, is the right long-term approach. A philosophy Tesla's Cybercab actually shares, even if the underlying technology stack is completely different. So, has Tesla already won this race outright? Not necessarily, and it would be dishonest to say so. Waymo currently has significantly more real-world autonomous ride-hailing experience under its belt. BYD currently sells more vehicles globally than Tesla does. Toyota brings decades of manufacturing reliability and quality control data that Tesla, frankly, is still in the process of building. Zoox and Amazon bring the backing of one of the largest logistics and technology companies on Earth. What Tesla does have is a very specific, very expensive bet that combining massive-scale single-piece casting with in-house battery technology and its own self-driving software stack will let it eventually undercut nearly every competitor on both price and production speed simultaneously. Tesla's long-term strategy. So where is all of this actually heading over the next several years? Tesla's stated ambition is for the Cybercab to eventually become the highest volume vehicle the company has ever produced, potentially exceeding the combined production numbers of the Model 3 and Model Y put together. Musk has suggested that with this new 50,000-ton casting technology, a single Gigapress could ultimately support producing enough structural components to effectively cast several vehicle bodies within a single coordinated operational cycle. Beyond the Cybercab itself, Tesla is reportedly exploring an even more radical idea: integrating color pigment directly into the raw material used for body panels during the casting process itself, rather than producing bare metal panels and then running them through a traditional multi-stage paint shop. If that technology matures into something usable at scale, it wouldn't just speed up production further. It could eliminate one of the largest, most expensive, and most environmentally demanding sections of any modern car factory, the paint shop, which typically requires enormous amounts of energy, water, and specialized ventilation systems to operate safely. Tesla's broader 5-year vision, based on public statements from Musk and Tesla's own investor communications, seems to center around 3 connected pillars. The first is driving vehicle production costs down dramatically through radical manufacturing simplification, of which this Gigapress is the clearest example yet. The second is scaling full self-driving technology to the point where it can reliably support a genuinely driverless robotaxi network operating at commercial scale. The third is continuing to expand Tesla's energy storage and solar products as a parallel growth business running alongside vehicle sales. Whether all 3 of these pillars actually mature on the aggressive timeline Tesla has projected is honestly still very much an open question, and Tesla's own track record on timelines gives plenty of reason for healthy skepticism. There's also a manufacturing philosophy angle worth understanding, because it explains why Tesla keeps chasing bigger and bigger casting machines instead of simply optimizing its existing production lines. Tesla has repeatedly described its long-term goal as building what it calls an unboxed manufacturing process, where instead of building a car as one continuous body moving down a single assembly line, different modules of the vehicle, front structure, rear structure, interior module, battery pack, are built in parallel on separate lines and then joined together at the very end. Tesla claims this approach, first previewed for its next-generation low-cost platform, could reduce factory footprint by roughly 40%, compared to a traditional assembly line, while also cutting production time significantly. The 50,000-ton Gigapress fits directly into that vision, because the fewer structural sections a vehicle is broken into, the simpler the final unboxed assembly step becomes. If the Cybercab's entire underbody can eventually be produced as 1 or 2 giant castings rather than dozens of separately built sections, joining everything together at the end becomes dramatically faster and requires far less factory floor space. Tesla has also hinted that lessons learned from scaling this 50,000-ton machine could eventually feed back into future versions of its higher volume vehicles, potentially including a next-generation Model Y or a long-rumored, genuinely affordable compact model priced well under $30,000. In other words, the Cybercab may end up being the proving ground for manufacturing techniques that later show up across Tesla's entire lineup, not just its Robotaxi program. That would mirror exactly how the original Model S pioneered technology that later trickled down into the Model 3 and Model Y, making premium engineering accessible at a much lower price point over time. The real challenges, risks, and honest limitations. Now let's slow down and talk fairly about the problems here, because this story genuinely isn't all good news, and a responsible breakdown has to include the downside. The first concern most people raise is repairability. If a large section of a car's body is one single giant piece of cast aluminum instead of dozens of individually welded components, what actually happens when just one small area gets damaged in a routine fender bender? Logic would suggest you'd need to replace the entire casting, which sounds like it could be an extremely expensive repair for something that used to be a minor fix. Interestingly, the real-world data available so far has pushed back against that assumption, at least for now. Thatcham Research, a UK-based vehicle safety and a repair research organization, published findings in 2025 following 2 years of crash testing, damage assessment, and hands-on repair analysis performed directly on Tesla's Model Y. Their conclusion was that Tesla's mega-casting rear structure was, in the majority of cases they tested, actually repairable rather than requiring a full and costly replacement. And in several tested scenarios, it was even cheaper to repair than a comparable multi-piece traditional steel structure would have been. That's a genuinely meaningful data point in Tesla's favor. Still, it's worth remembering that this research covered a 6,000-ton casting used on the current Model Y, not the far larger 50,000-ton components Tesla is now planning to introduce with the Cybercab. So it remains to be seen whether those repair outcomes hold up at this new, much larger scale. Second, there's the sheer cost and risk involved in scaling up something this untested. A casting machine of this size has never been mass deployed anywhere in the automotive industry before. If Tesla runs into unexpected engineering problems along the way, inconsistent cooling, unpredictable material defects, low production yield rates, or unforeseen wear on the mold itself, it could significantly delay Cybercab production, and Tesla has a well-documented history of missing its own self-imposed launch deadlines by a wide margin. Third, there's the regulatory and safety dimension of autonomous driving itself, which is arguably the single biggest hurdle of all. No matter how efficient and elegant the manufacturing process becomes, the Cybercab's entire business case depends on full self-driving, reaching a level of proven reliability and formal regulatory approval that allows it to operate completely without a human driver present, in a vehicle that physically doesn't even include a steering wheel as a fallback option. That's a substantially higher bar than anything Tesla has managed to clear so far, and regulators across the United States and Europe have both demonstrated a clear willingness to slow down or restrict deployment when meaningful safety questions remain unanswered. Fourth, there's a genuine workforce impact worth acknowledging honestly. If a single Gigapress can effectively replace the work previously performed by roughly 1,000 welding robots, along with the human technicians who maintain and oversee them, that inevitably has consequences for factory employment patterns, even if it simultaneously creates new kinds of technical jobs elsewhere in Tesla's manufacturing and engineering pipeline. Fifth, and often overlooked, there's the sheer capital cost involved. Tooling for a casting machine at this scale, along with the specialized furnaces, cooling systems, and quality control infrastructure surrounding it, represents an enormous upfront investment. If the Cybercab doesn't sell in the volumes Tesla is projecting, that investment becomes significantly harder to justify financially, no matter how impressive the underlying engineering turns out to be. Sixth, there's a question of quality consistency at extreme scale. Casting a component this large means any tiny inconsistency in temperature, pressure, or timing gets magnified across a much bigger surface area than Tesla has ever worked with before. Automotive analysts have pointed out that yield rates, the percentage of castings that come out defect-free on the first attempt, tend to be harder to maintain as component size increases, at least during the early ramp-up period of any new casting process. Tesla has generally improved its yield rates over time with its existing 6,000 and 9,000-ton machines, but there's no guarantee that same improvement curve will repeat itself cleanly at more than 5 times the scale. And finally, there's a broader industry skepticism worth acknowledging honestly. Several veteran automotive engineers, including some who previously worked at legacy manufacturers, have publicly questioned whether Tesla's aggressive part consolidation strategy sacrifices long-term structural flexibility for short-term manufacturing speed. Their argument is that traditional multi-piece body construction, while slower to assemble, allows for easier design iteration between model years without needing to redesign an entire casting mold, which itself can cost tens of millions of dollars to engineer and manufacture. Tesla's counterargument is that the speed and cost savings from consolidation outweigh that lost flexibility. Which side turns out to be right will likely take several more years of real-world production data to determine conclusively. Final analysis: breakthrough or overreach? So, stepping back and looking at the full picture, what's the honest, balanced verdict here? Tesla's 50,000-ton Gigapress represents a genuinely ambitious attempt to rethink how cars get built from the ground up, rather than simply making an existing manufacturing process marginally faster. The underlying engineering challenge is real and substantial. The potential. Cost savings appear significant if everything works as planned, and the early repairability data from independent researchers is more encouraging than many skeptics initially expected it to be. At the same time, this is genuinely unproven technology being deployed at a scale nobody in the automotive industry has previously attempted. Waymo currently has far more real-world autonomous driving experience logged on public roads. BYD currently outproduces Tesla in raw global vehicle volume. Toyota brings decades of manufacturing reliability and quality assurance history that Tesla, by comparison, is still very much in the process of building and proving out. Tesla's real advantage here isn't that it has already won this race. It's that the company remains willing to take a far bigger engineering swing than almost anyone else in the industry, backed by a manufacturing philosophy that has, on more than one occasion, forced the rest of the automotive world to catch up to what Tesla was already doing. Will this 50,000-ton Gigapress actually deliver on its ambitious promise? Will the Cybercab genuinely hit that under $30,000 price target while remaining profitable for Tesla at scale? Those questions won't be fully answered until Gigatexas ramps up real production over the next couple of years, and until Tesla's full self-driving software clears the regulatory hurdles standing between where it is today and a truly driverless commercial robotaxi fleet. One thing, though, seems fairly certain right now. The rest of the automotive industry is watching this experiment extremely closely, because if it genuinely works as intended, it won't just change how Tesla happens to build its own cars. It could change how every major automaker on the planet thinks about building cars going forward. So what do you think? Is Tesla's giant casting gamble a genuine engineering breakthrough that the rest of the industry will eventually be forced to copy? Or is this a case of Tesla overreaching on an unproven idea before the technology, and the regulations around autonomous driving are actually ready for it? Let us know what you think in the comments below. We genuinely want to hear both sides of this one. If you found this breakdown useful, go ahead and hit that like button. Make sure you're subscribed to Tesla Tech and tap the notification bell so you don't miss our next deep dive into the technology shaping the future of electric vehicles. Thanks for watching, and we'll see you in the next one.